How are y'all doing today?
Doing okay. How are you doing, Dr. Hartman?
Doing all right. So who's got a question?
Could we look at summer 2019, I believe, number 20? I think it's the graph, like the area under the curve. And I kind of see where you're going with, and I see how you get it, but I want to know if you can show me like the shaded area under the curve.
Sure, if my computer will behave itself. Don't know why it's not letting me select that screen. All right, give me just a second. So you said summer.
Yes, sir. Summer 2019.
All righty. What problem?
Yeah, that's it. Yes, sir. Just trying to see the area under the curve, the shaded region.
All right, so let's see. We're looking for the capacitor current, and we have the capacitor voltage. Let's see. So number 20, you said? Because number 19 is a derivative-based relationship.
Yes, number 20.
Okay, so at 2 milliseconds. So it's that triangle, which is 1/2 base times height. So this area is 1/2 the base, which is 2 milliseconds minus 0 milliseconds, times the height, which is 1 volt minus 0 volts. So that area is, let's see, 1 times, so 1 volt millisecond. So our wait, but why do we need the area at all? If we're trying to find power, we're never, okay, so here's the deal. All right, let me circle back to something. So our equations for a capacitor are I of t is equal to C dV by dt. And our voltage relationship is 1 over C integral from T naught to T IC of X dx plus IC, VC at T naught. We already know VC, and we're trying to figure out IC, so this is the relationship that we should be using. So for number 20, we would literally say, all right, so the slope of this guy, dV by dt, is going to be the change in height, which is 1 volt minus 0 volts, divided by the change in time, which is 2 seconds minus 0 milliseconds. So that is 1 over 2 times 10 to the minus 3, 500 volts per second. So from this, our current, not a lot of time, so I'll sneak it in here. So IC at 2 milliseconds is our capacitor value, which is 610 times 10 to the minus 6 So that's micro. And let's see, a farad is a amp second per volt multiplied by our slope, 500 volts per second. So volts cancels volts, seconds cancel seconds. Is 0.305 amperes. Our voltage at 2 milliseconds, we can see from the graph, is 1 volt. So if we multiply those two things together, we should get positive 0.305 watts, which is exactly what we get. So we should never have done integration on this problem to begin with, based on the information that we were provided.
Yeah, I think I got it switched up. I think it was supposed to be winter 2019-20, but that's fine. I see what you did there, and I can take it to the other one.
Okay. Yeah, so for the problems with integration, it's literally, they're always going to be right triangle, so it should be 1/2 base times height for the triangles and base times height for the rectangles, and then add things appropriately. All right, next problem.
Can you work summer 2019, number 24?
Number 24. Alrighty, so this is a DC circuit, which means this guy is a short circuit and this guy is an open circuit. And we need to find this current, let's just call that IL, and this voltage VC. So let's see. I'm going to redraw this just real quick. It might make things a little bit more clear about what's about to happen. And let's see, 7, 12, 17, 46 volts. Here's IL. Here is VC. All right, so let's find IL first. So I say telling me something weird here. IL is going to be 46 volts divided by 17 ohms plus 7 ohms. Is 1.917 amps. And the reason why I can say that it's just those two resistors in series is because the 9 ohm resistor is shorted out, which means it's not going to contribute anything. And that 12 ohm resistor has one leg free, so it's not going to contribute, like no current or branch off and flow to the right effectively. So from that, the energy stored by the inductor is 1/2 times 0.28 henries times that 1.917 amps quantity squared. Is 514.30556 millijoules. To get VC, I am going to do Kirchhoff's voltage law. So I could say that negative 46 volts plus 17 ohms times my 1.917 amps of current plus VC is equal to 0, where, to be clear, I'm just doing KVL around this loop. From this, VC is 46 minus 17 times that 1.917 amps is 13.417 volts. And the energy stored by a capacitor is 1/2 the capacitor value, 150 micro, times that voltage of 13.417 volts quantity squared. Is 13.501 millijoules, which I guess you weren't asked for the energy stored by the capacitor, but I figured it out anyway. Any other questions or anything?
I have a question on the winter 2019 exam.
All right, let me open that up real quick. Winter. All righty, which problem, sir?
Question 30. On the solutions, there's a negative 0.609 e to the negative 10, or a negative t over 0.065, and I can't figure out where the negative 0.609 came from.
All right, so y of t is y at 0 minus for t less than 0 minus, and it is y at 0 plus minus y of infinity e to the minus t over tau plus y of infinity for t greater than or equal to 0 plus. So y at 0 plus, according to my solutions, if everything is correct, is 2.058 amps. Y at infinity is 2.667 amps. E to the minus t divided by tau, which is 65 milliseconds, plus y at infinity, 2.667. .058 minus 2.667 is negative 0.609 e to the minus t over tau plus 2.667.
Okay.
Just putting the answers to the previous problems in the proper equation for the generic response of a RL or RC circuit.
I got you. Thank you.
Yep. Next question.
Can you work number 23 from the same test? All right, let's see here. Okay. So this 27 and this 36 are in series, right? So 27 plus 36
makes it 63. That 63 is in parallel with this 79. Which means this guy right here is 35.05 effectively. We do the same thing down here at the bottom, 15 and 34 in series, which makes 49. That 49 is going to be in parallel with 43. Which means this guy right here is 22.902 millihenries, and the 35.05 is in series with the 22.92. Do you see that?
Yes.
So that's 57.95, which is in parallel with that 60. So all of this crap looks like 29.479 millihenries. Now the 41 is in series with that 29. So plus 41, meaning that we have 70.479 in parallel. I'll get to that in a second here. So 41 in series with 29.479 looks like 70.479. And that is in parallel with the 57. Which gives us 31.513. And then the 30 and the 51 are in series with that 31.513. So that's plus 30 plus 51 gives us 112.513 millihenries.
Thank you.
Yep. I think maybe the hardest part about this problem is recognizing that this 41 and this equivalent resistance are in series, at least unless you read all a bunch of times, it may not be super obvious. All right, so there was a question in chat. Where did it go? How would I define energy, power, and charge? I don't particularly understand the question. And so what I mean by that is like, as it pertains to what? Charge fundamentally is 1.619 times 10 to the negative 19 coulombs is the fundamental unit of charge. Every electron has negative that, every proton has positive that. Charge is a quantized quantity because there can only be whole numbers of electrons and protons in a particular material. Power is the rate of energy transfer, either to or from a circuit element or something like that. Energy is the amount of work done. Question like number 8 on the 2019. Let's see. The electrical quantity which describes how a circuit changes to, or a circuit reacts to a changing magnetic field is inductance, and it's measured in henries. The electrical quantity which describes how a circuit reacts to a changing electric field is capacitance. The definitions for energy, voltage, power, and current are all in the very first lecture that was given in this class. And conductance and resistance would have been in the Ohm's law and Kirchhoff's current law and Kirchhoff's voltage law lectures. And then the definitions for inductance and capacitance would have been in the capacitor and inductor lecture. Next question.
Could you work number 21 on the winter exam?
Sure, let's take a look at it. All right. So looking for the power at 8 milliseconds. So let's see what we got here. So we have the current flowing through a capacitor, which means we're going to need to find the voltage where charge should have been in lecture 1 as well. All right, so the voltage drop over a capacitor is 1 over C integral from T naught to T of IC of X dx plus VC at T naught. So we are going to need to use our areas of triangles kind of thing here to figure out what's going on. So at 8 milliseconds, okay? So let's call this area A1, this area A2, this area A3, this guy A4, A5, well, this one's going to be tedious, A6, A7, A8. So we're going to have 1 over C, 185 microfarads times A1, which is 1/2 the base, which is 2 milliseconds, times the height, which is 4 amps, plus A2, which is, let's see, the base is 1 millisecond, and the height is -2 amps, plus A3, so that's just base times height, so that is 2 milliseconds times 2 amps, plus A4, it's triangle, so 1 milliseconds, the height is 1 amp, A5, 1/2 the base of 1 millisecond times the height of 3 amps, A6, triangle, so 1/2 the base of 1 millisecond. The height is -3 amps. Plus A7, so that is 1 millisecond times -2 amps. Lastly, that last triangle, A8, is 1/2 1 millisecond, -1 amp. Close this whole thing off and solve for that, and this gives us V at 8 milliseconds. So let's see, 0.5 times 8. Oh, I'm missing, sorry. There should be a 1/2 here as well that I forgot. Because A2 is a triangle. Minus 0.5 times 2 plus 4 plus 1 plus 3 halves minus 3 halves. Those two guys canceled out. Minus 2 plus, sorry, minus 1/2. 5.5 amp milliseconds. So just to be clear here, we're going to have 1 over 180 multiplied by 5.5 times 10 to the minus 3 amp seconds gives us voltage of 29.730 volts plus our initial condition there. So 35.73 volts multiplied by the current, which is -2 amps, -71.459 watts. Let me see what all is going on in chat here. All right, yes, the exam starts at 6 p.m. It is in IESB 212. So exactly one story up from where the circuit class is taught. All right, next question.
I have a general question.
Okay.
So when is it the appropriate time to use like whenever it comes into these questions like Norton's or Thevenin's, I forgot to say can't really say the name, but when is it appropriate to use like your own voltage source? So like plugging in a 1 voltage source. So I believe this is the summer exam that we're currently on, correct?
I think we're on the winter exam. So let's
We're on the
see.
winter exam.
Yeah.
All right, so if you go to number 13, oh, this is the summer. So go to number 4. Oh, actually, this is the question. So whenever I was trying to solve this problem, I didn't know if I want to put in my own voltage source and put like one voltage source or my own current rather than solving for like nodal analysis or mesh analysis. Like,
So for this particular problem, number 13 here, we're all looking at the same thing, I hope, right? So for this problem, you're asked to find the Thevenin voltage, and then you're asked to find the Norton current. You only use a test voltage source or a test source when you are trying to find the Thevenin resistance of a network, okay? So for this particular problem, if we wanted to find the Thevenin resistance directly, we could apply our test source, be it a current source or a voltage source, but we would also have to turn off all of the other independent sources in the circuit. If we look at the summer exam, problem 15 here, there are no independent sources in the circuit at all. So our only methodology to find the resistance is applying our test source, where in this case, it would make the most sense to apply a test voltage source because that means we've defined what Vx is.
Okay, then what would you do if we need to apply a current test source?
So
If you
for a
did-
current test source, why won't, is my pen thingy writing? Hold on just a second. So a 1 amp source like so, Vx would be exactly the same as Vtest because the positive polarity terminal on Vtest should correspond to where the arrow is. So for this guy, just using this, we would have, let's see, I don't even know if I would call it mesh per se. No, let's do nodal, right? Where our top node is Vtest. So we would have -6 Vtest flows out plus Vtest divided by, sorry, flowing out should be positive. Vtest over 16 ohms is going out minus 1 amp is equal to 0. Solve this guy for Vtest real quick. So 6x plus x over 16 minus 1 is equal to 0. Solve. Vtest is, taking my calculator forever, 0.165. Or 164948 blah 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 volts. RTH by definition is Vtest over Itest, which is 0.165 volts over 1 amp is 0.165 ohms.
Awesome, thank you.
Yep. Next question.
Dr. Hartman,
Yes,
did you say you only use V-test when you're finding the Thevenin resistance?
that is correct. Only when
Okay.
finding Thevenin resistance. Never
Okay.
when finding Thevenin voltage or Norton current.
Thank you.
Dr. Hartman, this is just a general question, but when is it best to use like forced response versus total response or natural response? I'm sorry, natural response.
So if we look, there is a, let me pull up a sheet of paper real quick. All right, so very generically, let's say that we have a very simple RC circuit where this is our source voltage. We have a switch. Here's our resistor. Here is our capacitor. This is a natural response problem because the source is being taken out of influencing the capacitor, okay? The total response problem would be the exact same circuit. Now our switch is closing. So we have a total response problem whenever the source is left in, and we have a natural response problem whenever the source is taken out. Now, let's look at the equations for the response here. For a natural response, we have y at 0 minus, for t less than 0 minus, y at 0 plus, e to the minus t over tau, for t greater than or equal to 0 plus. And then over here, we have y at 0 minus, t less than 0 minus, y at 0 plus minus y at infinity, e to the minus t over tau, plus y at infinity for t greater than or equal to 0 plus. Okay, so if we use the total response equation on a natural response problem, the only thing that we're going to find out is that y at infinity is 0. So I would argue that if you have trouble differentiating between the two types of circuits, use this guy and just take the extra step to find out that y at infinity is 0. You won't get the answer wrong. Whereas if you treat a total response problem as a natural response problem, you will absolutely get the answer wrong. So this guy works for both total and natural response. This guy doesn't.
Thank you for that. That cleared up a lot. Thank you.
Why is 5 the minimum number of time constants? 5, I don't particularly understand your question, but let's talk about the concept of time constants real quick here. So a time constant is nothing more than a number that represents effectively how long it takes for a signal to decay to some specific value, right? So one time constant is how long it takes for a natural response to decay to, let's see, calculator out here so I can give you a precise number. .788% of its initial value. So if we looked at this RC circuit that we had up above, and we plotted the capacitor voltage as a function of time. So VC, and here is our time axis. It's going to look something like this, right? It's just exponentially decaying, getting smaller and smaller and smaller, etc. This is VC at 0, the initial value. If this is 0.36788 VC at 0, this is exactly 1 tau. And 2 tau occurs when effectively we have VC at 0 multiplied by e to minus 2. So e to the minus 2 is 0.135, that looks like a 3. 0.13533 V at 0 is 2 tau, et cetera, et cetera, et cetera. So if we made a table, just for the sake of argument. The number of time constants versus VC of t. At 0 time constants, we have Vs. At 1 time constant, we have 0.36788 Vs. At 2 time constants, we have 0.13533 Vs. At 3 time constants, sorry. We have 0.0498 Vs at 4, 0.0183 at 5, 0.00674, et cetera, et cetera, et cetera. Engineers consider 5 time constants to be infinity because the signal has decayed to less than 1% of its initial value. Because 0.00674 means we're at 0.674% of what it started at. Did that answer your question at all? Or, yeah. Yep, cool deal. All right, next.
Okay, I have a question, and it's kind of long, but okay, so is it that, you know how like V minus or V of 0 minus and V of 0 plus sometimes doesn't change instantaneously, and then I of 0 minus and I of 0 plus don't change instantaneously? Is it the voltage doesn't change when it's a capacitor and the current doesn't change when it's an inductor, or did I
That
make
is correct.
that up?
That is correct. Nope,
Okay.
that is absolutely correct.
I couldn't find it in my notes, so I was starting to think I just made that up.
Nope. The current through a inductor cannot change abruptly, so I at 0 minus must be equal to I at 0 plus. The voltage drop over a capacitor cannot change abruptly, so that means it's V at 0 minus must be equal to V at 0 plus. All right, here, let's see. Winter, the last two on the winter diagram. So let's see, this is the winter. Oops. I'm 99% sure they both are total response, but I will explain why. All right, so the reason why this one is a total response is because when the switch closes at t is equal to 0 plus, this 8-volt source is connected in some way, shape, or form to the 150 millihenry inductor. So it is a total response problem. When we look at number 31, when the switch closes here, this current source is still connected to the capacitor, so it is also a total response problem. It's only a natural response problem when the sources get taken out of the circuit containing the capacitor or the inductor. All right, next.
Could you go over 25 on the summer test?
All righty. All right, I'm gonna have to erase some of this junk up here because I don't have enough. All right, what I'm going to do first is define the voltages. So I'm going to call this guy VR with respect to time, and I'm going to call this guy VL with respect to time. And I've chosen those polarities so that my current IS is flowing in the positive polarity terminal. Okay. So generally speaking, I can say that Vs of t, the voltage drop over my source, is equal to Vr of t plus Vc of t plus L of t. That's just Kirchhoff's voltage law around my circuit, where Vr of t is R times Is of t. That's just Ohm's law. Vc of t is 1 over c integral from t naught to t of Is of x dx plus Vc at t naught. Sorry. So that's my current voltage relationship equation for a capacitor. And lastly, the L of t is equal to L times dis by dt. Now we are asked specifically to find Vc at t is equal to 0. So I would argue that Vs at 0 is equal to Vr at 0 plus Vc at 0 plus VL at 0. So this is simply stating that Kirchhoff's voltage law must be true at t is equal to 0, which it has to be. It has to be valid at all points in time. And so from this, I could say that Vc at 0 is simply Vs, which we know, minus Vr at 0, which we don't know, minus VL at 0, which we also don't know. So I'm going to put in, let's see, 26 volts right there. So Vr of t is simply 5.1 kiloohms times that current. So 5.1 kiloohms times 18 milliamps gives me 91.8 e to the minus 25,000 t volts. Is there a way to do this without KVL? I don't know, but I don't know. This is the way I'm doing it. So now that we know what Vr at 0 is, we can put that in. So minus 91.8 volts. VL of t is L times di by dt. So L in this case is 25 millihenries. So that's times 10 to the minus 3 volt seconds per amps. When we take the derivative of our exponential function, this is going to be minus 25,000 units per second. And this is being multiplied by the stuff I'm writing on the next line because I'm running out of room. Multiplied by our current of 18 times 10 to the minus 3 amps times e to the minus 25,000 t. So look at the units here, just to be clear. This second cancels this per second because seconds multiplied by per second cancels out. This amps cancels this. And so we have 25 times 10 to the minus 3 times negative 25,000 times 18 times 10 to the minus 3 is negative 11.25 volts. So minus negative 11.25 volts. This is going to give us 26 minus 91.8 minus 11.25. Negative 54.550 volts. Which is that? This is extraordinarily similar to a problem on homework step number 12. Next question.
Are those integrals going to be given to us in the test, or do you have to memorize them?
You have to memorize them. So to be clear, let's say that we have an inductor. Here is the voltage over the inductor. Here is the current flowing through the inductor. Our relationships are VL is equal to L di by dt. We rearrange this guy, we get IL is equal to 1 over L, the integral from T naught to T of VL of x dx plus IL at D naught. Power absorbed by our inductor is always voltage multiplied by current, which will be L I di. And lastly, energy is 1/2 L IL squared. Now let's say that we have a capacitor. Here's our voltage drop. Here's our current. Inductors and capacitors are electrical duals. That means that everywhere I see voltage in my inductor equation, I can change that to current. And everywhere I see inductance in my equation, I change that to capacitance. So that means we're going to have IC of T is equal to C dV by dt. Vc of T is equal to 1 over C IC of x dx plus Vc at T naught. I'm not going to write I times V for power for the capacitor because I'm kind of running out of room here. I times V is always power, so don't forget that. C Vc dV. And finally, energy 1/2 C squared. So those are the 8 equations you're expected to know regarding how the relationships for inductors and capacitors. This is the other relationship, transient analysis circuits. So those are all the equations. And these are effectively identical. You can just change the I's, or transpose the I's and the V's and the L's and the C's.